Okay, well, it's my pleasure today to introduce our water talk speaker, Dr. Larry Ostresh, who's a professor of geography at University of Wyoming. I've noticed that he's been on the faculty here since 1971, which is becoming a rarity. I saw the other day where out of the 630 faculty on campus, 240 have resigned since 1963. So we thank you, Larry, for hanging in there. Larry's specialties have evolved as the technology of computer cartography has evolved. Today he lists computer-aided mapping and geographic information systems as his primary interests, although he tells me his interests range over the entire breadth of geography. I think it's worth noting that Larry received a grant recently, a major equipment grant from the Dunn estate to establish a computer cartography laboratory in the Department of Geography. And he's using this to teach a number of courses, as well as to design the computer-generated Wyoming Atlas, which is the topic of his talk today. So, Larry?
Thank you very much, Dick. Water is critical in Wyoming, as it is throughout much of the American West. About a year and a half ago, the Wyoming Water Development Commission issued a request for a proposal for methods of informing the general public about the general public, the state legislature, state and federal agencies about the nature of water issues in Wyoming. This would help them formulate policies regarding the use, the development, or perhaps conservation of this most precious resource. Richard Marston, who introduced me, myself, and a graduate student, Walter Hudson, all of the University of Wyoming Geography Recreation Department, responded to this request for a proposal with a proposal to develop an atlas, a water atlas, that was computer generated. As many people realize, a map is the most efficient and effective means of portraying spatial information, and water data is inherently spatial. As researchers, we were also anxious to test the capabilities of computer graphics as applied to map construction. A little over a year ago, we were given the go-ahead to pursue such a task to create this atlas, and today's report is more or less a status report of how we've come along in the ensuing year. Computer mapping has come a long way since the early days of CMAP or SciMap. This came out in the late 1960s and created maps done on a plain old ordinary line printer. They were fairly crude, but they were the original maps to come out, be produced by computers, and they were the state of the art for a good many years, well up until the early 70s, I think. An advance over that was a device, a plotting device called a CalComp plotter, which allowed a map maker to emulate the actions of an actual cartographer. Lines, in other words, could be drawn. Different sizes of lines, different styles of lines. This led to great growth of what was called vector graphics. Vector graphics being essentially lines drawn on a plotting device of some sort. And even today, vector graphics, vector plotting, vector mapping is the major means, in fact, the method of choice of most computer mappers and geographic information specialists. The relatively low-cost availability of the hardware and the software more or less make vector graphics this method of choice. We can use vector graphics to create maps with a considerable amount of appeal. Let me give you some examples. If we could have the slides, please. I don't seem to be able to focus it from here. Great. This is an example of a vector graphic output. It was done here at the university using a plotting device called a COM recorder, computer output to microfilm. This is a device that we were fortunate enough to get in the good old days when Wyoming had money. The device itself cost about $500,000, and for those of you who are interested in esoteric trivia, the device that we have put out by a company called Triple I, it's an FR80A, COM recorder, computer output to microfilm plotter. It turns out that our machine is a sister machine of the machine that created the Walt Disney movie Tron. Well, those were the good old days. An example of computer output using the vector device, essentially a series of line drawings. The advantage that the computer has is very rapid creation of such devices, sufficiently rapid that we can create several slides, put them in sequence, and watch my favorite soap opera as the world turns. Looks like we've lost focus again. John, if you could. Oh, well.
The knob seems to be slipping on the lens.
Okay. Well, then we'll look at it out of focus. Once we've got a continental outline database, next thing we want to do is put some data on top of it. In this particular sequence, I show sizes. I show little people, is what they actually are, the red symbols around there. And it shows the relative sizes of people in various major regions around the world. So we can not only do continental outline type maps using vector methods, we can also put data on them, in this case a proportional symbol device. This shows the growth of world population from the 1650s in 50-year increments, 1700, 1750, 1800, 1850, 1900, 1950, projection to the year 2000. Rather dramatic change in the way that that people are distributed around the world, and significantly their amounts. All these people put great stress on the natural resources of the earth to take care of these people. Another example of the vector method. Yet a further example of the vector method. This is a so-called Choropleth map. The Choropleth style of map is probably the most widely used mapping style using vector graphics nowadays. This shows a sequence from the Rocky Mountain states. 8 western states were labeled for your orientation: Montana, Wyoming, North, South Dakota, Nebraska, Colorado, Utah, New Mexico. See what a degree in geography will allow you to. This shows the growth of crime in the 8 western states in the early 70s, when we had a major crime surge going on throughout the United States. This is 1970, 71, 72, 73, 75, and 76. Rather strong change in crime rates throughout this Rocky Mountain region. Again, another example of the capabilities of vector graphics. And this is pretty much what is most widely used in terms of computer mapping bases throughout the United States, throughout Canada, indeed throughout the world. Such maps can, in a rough way, portray landforms. Here we go on an airplane ride around Driggs Quadrangle in the in the northwestern portion of the state, better known to most of us as Jackson Hole. And this is one further and one last example of vector graphic output. Some 22,000 urban locations around the United States. The interior west has been called the empty quarter for a very good reason. It's relatively quite devoid of population. One of the limitations of vector graphics is that it's restricted essentially to what a person can draw more or less directly, or by analogy I should say, with pen and ink, and that's about it. You go from one place, you put the pen down, and you draw it. If you make a mistake, it's very, very difficult to go back in vector graphics and erase it. Some of the slides that I showed earlier, but for example, the people on top of the, or the symbol for the people on top of the continental base, if you looked at those people and the continental outline happened to be behind them, you saw right through it. That is a fundamental limitation of vector graphics. There's another style that is probably the state of the art in computer graphics as opposed to computer mapping. And that style is called raster graphics. In raster graphics, you have essentially the complete freedom to overlay one object on top of another. It's very, very simple to solve what are called hidden line problems. If the line goes behind me, you don't see the line because I'm in front of it, that sort of thing. This next slide is an example of that same data, but shown this time in a raster method. And in particular, what I'm using as the background of this is the topography of the United States. Topography is a key geographic variable and turns out to be related to many other kinds of variables as well. As we were in the design phase, or in fact as we were deciding what we would put into our proposal, we decided that that raster graphics was the approach that we would attempt to use in this water atlas. Primarily because we felt that the topography was sufficiently important in a state such as Wyoming that we should include it wherever possible. That the simple mapping of water information, other information on top of the topography, because the base was there, the topographic base, that would help to explain that relationship. On a very simple level, let me draw your attention to a couple of geographic features that pop out from the topography right here. First off, the plains over here tend to have more people than the mountains over here. On the west coast in the Central Valley, we see the same thing applied. Thus, topography, to a certain extent, just at a very crude level, is one of the key factors in explaining the distribution of people in the United States. Obvious other key factors, the mountains are not only mountainous, we get increasingly dry as we come over here toward the mountains. Water, precipitation, is another key variable affecting the location of people. On a somewhat more local level, but still of a great historic national importance, let me draw your attention to the area over here, the northeastern seaboard, population center in and around the city of New York. One can argue, I think, with some claim to validity, that the reason for the primacy, or historical primacy, of that particular location in the United States in terms of people, economic power, political influence, and so forth, has to do with what shows up as a red band straight across here. This red band, of course, is a whole series of cities that come along this corridor. The corridor turns out to be a topographic low portion through the Appalachians, allowing more or less of a water level route between the port cities of the East Coast and the interior developing heartland, if you will, the agricultural heartland of the United States. Here's a close-up of that corridor, the Mohawk corridor, through which the Erie Canal was built to link New York with the remainder of it. Hoping to make the point that, at least in certain cases, topography is an important variable, should be included, if possible, in other kinds of maps. The remainder of my talk and the remainder of my slides come essentially, in fact, all of them, come from the Wyoming Water Atlas as it's progressing so far. I'm the cartographic programmer. Richard Marston is the text editor. Walter Hudson is responsible for the cartographic designs. The background on this, water atlases of other states are quite common. There was no existing water atlas for Wyoming. Well-designed, produced atlas is the best way of communicating information on water issues. Funding for the design and publication of this atlas by the Wyoming Water Development Commission, it was funded by the Wyoming Water Development Commission through the auspices of the Wyoming Water Research Center. The scope of our project, the atlas, was to produce a computer-generated water atlas and select the topics for this atlas in conjunction with the Wyoming Water Research Center, the Wyoming Water Development Commission, the Wyoming State Engineer's Office, and most importantly, to use existing published information. Within the scope of the atlas, we were not to go out and collect new data. We were to use what data already existed. Our methods were to use a base map from Digital Elevation Model, or DEM, supplied by the U.S. Geological Survey. Let me back up just a tad here. The base map is essentially a series of elevations. In the case of Wyoming, we used two different elevation files. One of them has well, if you imagine Wyoming being divided up into small portions of latitudes and longitudes, then for the Wyoming database that we use for the bulk of these maps, we have a row of elevations, or excuse me, we have 481 rows of elevations. Each one of those rows has 841 columns. That comes to something on the order of 400,000, a little in excess of 400,000 different elevations for the state of Wyoming. On one of the maps that I'll show you in just a minute, shows the entire United States. That comes from a far more extensive data set. Instead of having only 400,000 points, it's got something on the order of 20 million. So the volume of information, in other words, is quite large. This was our database. Fortunately, we didn't have to go out and gather all 400,000 elevations on our own. The U.S. Geological Survey did that for us. But we did have to digitize significant amounts of information. Polygons is maybe a too technical word here, but if, for example, if we wanted to include water drainage basin boundaries, then we had to get those boundaries into the computer in some fashion or other, and that process is called digitizing. So suffice it to say that there was a significant amount of digitizing that went on in the creation of this atlas. Most of the software that we needed to run the programs was developed here on campus and already existed by the time that we were applying for the grant. We did have to do some minor amounts of additional programming, however. The organization of the atlas will come in 3 phases. By the way, at the end of my talk, I do have an outline of the atlas that I'll be glad to pass out. You may keep, and it will serve as more or less documentation of what we will be putting into the atlas. I won't be showing you everything that we've done today. But the basic organization of the atlas is a series of statewide maps, 36 of them, a series of drainage basin maps. These are blow-ups of the state, so that we're only looking, say, at about a quarter of the state in any one slide. And then followed up by the only non-computer generated maps in the atlas, namely what amounts to an appendix of flood hazard maps. These were put out by the Federal Emergency Management Agency, FEMA, and we're simply taking their maps and putting them into the atlas, including them as part of the atlas. The statewide maps, well, I won't dwell on this. We'll simply start looking at them. We start off with this slide. This will be essentially our first map. We call this Wyoming Headwaters of the West. And on this, we have the state of Wyoming outlined. You can see it there in the yellow. The orange bands that crisscross around there are the major drainage basins of the United States. And Wyoming literally is the headwaters of about 1/3 of the contiguous United States. It's an enormous area. It includes the upper Colorado, the Colorado green here, the Snake River drainage, most of all the Missouri, and a very small portion of the Bear, which leads into the Great Basin, I guess, which interestingly enough has no outlet to the west. It simply drains, in this particular case, into the Great Salt Lake and evaporates. Most of all, of course, most importantly, we drain into the Missouri. This is a close-up of Wyoming, showing the hydrography and the major drainage basins. Perhaps in many ways, historically the most important drainage basin here is the least auspicious in many ways. Just as the Mohawk Corridor provided a link between New York and the emerging Midwest back at the early start of the century, so that least significant in many ways drainage basin of Wyoming, the Great Divide Basin, which sits absolutely astride the Continental Divide, unique in that respect, provides a corridor from the east coast to the west coast. It's a topographic low area, very, very gentle rise, as anyone who's driven across the Red Desert is aware of. Not particularly interesting to a lot of people, but because of the presence of that topographic low and the basin that entails, Wyoming is the corridor to the nation. The artery of the nation goes right through here. The Union Pacific Railroad is the main line linking east and west. Highway 80 is the major truck route linking east and west. Far more used than any other corridor in the United States. That is the essential crossing of the Continental Divide. This shows the counties and the major cities superimposed on the topography. In many cases, the county boundaries in Wyoming tend to follow the divides. We see that along the Wind River Range right here. We see it in and surrounding Hot Springs County there. Even much more locally, Albany County tends to follow along the divides there. The cities, on the other hand, not surprisingly, in the arid west, tend to follow along the major rivers. The slides that I've shown so far are what are called planimetric, a straight down view. This particular slide right here is what we call a perspective view. The same software that does the planimetric can do a perspective. We have simply chosen, for the most part, to put the bulk of our maps in a planimetric manner. In this particular case, a very, very colorful slide, we're showing the geology of the state. Much of the topographic character can in turn be explained by the underlying superficial geology. The ancient granitic cores, such as here, the browns, and here, along here, show as topographic highs. But so interestingly enough, do the much more recent volcanic type geologic surfaces that we see up there in the vicinity of Yellowstone. John, if you could focus that just a tad. Thank you. This is the soils, major soil groups, and the impact of topography comes through very loud and clear on this one. The blue are the mountainous soils. They are acidic. The green, over on the right-hand side of the map, are the prairie soils, prairie grassland type soils. The yellows and browns are the high desert or cool desert soils, and the reds and oranges in the Bighorn Basin and somewhat to the south, in other words up here, are the somewhat different warm desert, lowland desert type soils. I'll just go on past that. This shows the natural vegetation of Wyoming. Again, a strong relationship to the topography. The blue, for example here, are the spruce fir forests, somewhat lower down elevation-wise. In other words, the green, for example here and over here, are the pine forests. The bulk of Wyoming is in this brown and yellow sage-type desert, natural vegetation. And something that I think will change in terms of color schemes, the grasslands over here in the red, red to me doesn't suggest grasslands. So I think we'll go to somewhat of a more yellow color sequence on there, which is fine. One of the key advantages of doing things on a computer is if you don't like a color scheme, it's very, very easy to change it, unlike if you're doing it by hand. This shows the precipitation around the state. We've chosen cool colors, the greens, the cyans, the blues to represent higher areas of precipitation, and the yellows and browns and oranges to portray the drier areas, those areas of lower precipitation. Again, very strong relationship to the topography. This is, if you will, the opposite of precipitation. It shows potential evaporation, how much it's evaporated and transpired by various plants. In other words, precipitation being given off to the atmosphere. Again, strong relationship to the topography. Same type of color scheme as in the previous slide. Greens, blues for the drier areas, in other words, areas of higher potential evaporation. Oranges, yellows, reds for areas, I'm sorry, got that backwards. The blues and greens, etc., lower areas of evapotranspiration because they are wetter. The reds, oranges, yellows, higher areas of evapotranspiration because higher levels mean drier areas. Now, an additional key aspect of doing things on a computer is we have, in this case, water coming in, or in the last slide, water coming in this slide, water leaving. It's all numbers, so we can manipulate those numbers. We can take the water that comes in, subtract the water that comes out, and voila, we have the water balance. And it's not a map that we have to recreate. We simply take two existing maps, quite literally, subtract the values at each point, and we get this. This shows water balance. In many ways, this is the key map in the Water Atlas because it demonstrates more than any other, I think, the critical nature of water in a state such as Wyoming. The blues and the greens, here and here, are the only areas on the map that have a positive water balance. More water comes in than leaves. All of the rest of the state is in a negative water balance, which means more water leaves than comes in. The impact of that upon agriculture is profound, because if you look at the places where we have a positive water balance, they're also cold. The water, or the growing season, is too short to support agriculture in the places where there's enough water for agriculture. Thus, the virtual impossibility of any kind of non-irrigated crop growing agriculture in a state such as Wyoming. As a matter of fact, over 90% of the whole state is in a negative water balance. This is a somewhat different kind of a map. What it shows is 100-year peak flows of the various streams and creeks around the state. The height of these little ribbons, we call them fences, is proportional to the amount of flow. And I think we're going to have to tamper a little bit with the color balance on here. Some of the things are just a little bit hard to see. I'm not sure, in fact, I can see them up here, but perhaps you cannot back there. On each one of these fences, you can see it perhaps more clearly along here. There's a little line, and each one of those lines represents a specific amount of flow, so that a person can look at the map and actually count up the amount of flow going through the 100-year peak flow going through. The one that stands out, of course, is the Powder River. It's got the highest recorded floods of any of the rivers of the of Wyoming, but a somewhat more interesting one to watch because it tells us something about what happens in the dynamics of streams is the Platte, which is this one right here. And in particular, I draw your attention to the peaks and troughs going along there. The troughs result just after a reservoir. So reservoirs have the effect of smoothing out the flood sequences, which of course is, I suppose, one justification for having dams and reservoirs in the first place. Excuse me just a second. We now enter a series of maps that show water data superimposed as a series of silos, I guess you'd call them. A silo for each of the major drainage basins. There's 18 such basins around the state. In this particular case, we're showing the total amount of water that would leave Wyoming under natural conditions if the people of Wyoming did not use any water. The height of these is proportional to the amount of water that would be leaving. The bands on the silos are at 500,000 acre-feet, so that, for example, in the green drainage, this one right here, 500, 1 million, 1,500,000, 2 million, about 2.4 million acre feet of water leaves the green drainage basin, or would do so under natural conditions if we didn't use any. So that's the amount of water leaving Wyoming. Wyoming, for the most part, is the main contributor to this. Wyoming gives most of the water there, but we also get some from other states. We get a little bit from Colorado that feeds into the Platte. We get a little bit from Utah, in particular the Uinta Mountains, that comes in, if you will, in the back door and enters the green before it goes right back down into Utah. But on the other hand, the amount that is contributing to this total outflow, the amount contributed from other states, is virtually insignificant. This is the total leaving Wyoming. This is the total that Wyoming contributes. And the two slides are virtually indistinguishable. Again, my point is that most of the water leaves is water that has been that has precipitated into Wyoming. Now, on the other hand, this is the amount of water contributed to Wyoming to that outflow. This is the total amount that leaves Wyoming after Wyoming has taken, quote, its share. And again, my point is that there's not a lot of difference from the last slide. Of most of the water that Wyoming contributes to the outflow, most of it actually does leave. We use rather little of the amount of water that we are given. The green, for example, shows hardly any change from the last slide. The Platte over here is reduced about 1/5 of what it was. The Bighorn up here is about 5/7 of what it was in the previous slide. And in the remaining drainage basins, hardly any use at all. Well, we do use some. And where does it go? For the most part, it goes to irrigated acreage. Now here, I've changed scales. On the last three slides, my bands were 500,000 units each. On this, I'm knocking those down to about a third, 150,000 units each, 150,000 acre feet, which means that graphically, while these are larger, they're in fact representing smaller amounts. This shows the distribution of usage in the major basins by This shows the total depletion in the various basins around the state. The Platte is large. The Bighorn in the top center is the largest by far. Some comes out of the green. Most of the usage here comes from irrigated agriculture. Compare this slide, which is total depletion, with the next slide, this one, which is depletion due to irrigated agriculture. Not much difference. Most of the usage, in other words, is due to irrigated acreage. The depletion due to irrigation, in the case of the Green River, here is about 300, or nearly all of the total of usage. In the case of the Bighorn, it's over 1 million. A million acre feet, which is again nearly all of the use that we make of it. In the case of the Platte, 4/5 of the water that is used goes to irrigated acreage. Most of the rest of depletion goes to reservoir evaporation, and here again I've kind of played a trick on you. I've changed the scales of things. The units here effectively make data from the following slide appear 3 times higher than it would have in the other. In other words, I've shrunk the values of each one of these little bands here. This shows the bands here represent 20,000 acre feet, and this is due to reservoir evaporation. In the case of the Platte, that's by far the largest. We're using about 200,000 acre feet or 200,000 acre feet of water goes into reservoir evaporation, compared to 600,000 being used for irrigated agriculture. So about 1/4 of that, or about 1/3 of the amount that goes into irrigated agriculture has to go into the reservoirs that support that irrigated agriculture, if you will. Bighorn, it's somewhat smaller, about 100,000 acre feet. Generally in Wyoming, a very small amount of water is used for municipalities and industries. Again, we go through a change of the scale here to, if we had stuck with the original scale, the little silos would be too small to see the difference, which is why we keep expanding them. In the case of the green, which is the major one, we use about 30,000 acre-feet of water for municipalities and industry. By far the largest user there is the Jim Bridger power plant. In the case of the Platte, the major user there is the Glen Rock power plant and the Wheatland power plant. This shows irrigated acreage. In the amount of irrigated acreage in the various counties around the state. And to a large extent, if a county happens to be on one of the major streams, so also is it using, or is its land quite extensively put into irrigated agriculture. We see that on the counties that more or less follow the Platte. We see it in the Bighorn Basin counties. Most particularly, however, we do not see it in the case of Sweetwater County. Sweetwater County has a very large amount of water but flowing through the green, but a very, very small amount of that water going into irrigated acreage. One reason for that one could speculate is because the water that could be used can't be used because of various interstate water compacts, the Colorado Compact in particular. As a matter of fact, that is not the case, as this next slide shows. This is in many ways the bottom line, if you will. This shows the amount of unappropriated water available to Wyoming. This is the amounts that could be used in the various basins if the state were to decide to do so. And the Bighorn Basin is by far the leader there. A substantial amount of water, however, is available in the Green River Basin, including Sweetwater County.
What's the scale?
The scale here, 200,000 acre-feet. So we've got 200, 400, about on the order of 800,000 acre-feet here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 times 2, close to 2 million acre-feet available in the Bighorn Basin. This in some ways might be a prediction for the future. This in some ways might lead people to think, well, let's do something here. It may not, and it may lead to rather substantial conflicts about should we not use that water. And it's in the illumination debates exactly like that. That's the whole purpose of I think, our water atlas, to help give people the information to help them to decide what might be an appropriate policy. But those are the basins to watch, I think, in the future. Keep your eye on them. If they're not in the news now, they will be. Water is used for far more things than industry, than irrigated agriculture and so forth. This is a map that shows the location of a series of something on the order of 1,600 people responded to a sample survey and told us where they fished. We mapped this, and not surprisingly, they're not fishing in the middle of deserts, of course, but certain areas do stand out rather well. Large dominance of fishing in the Jackson Hole area. The Green River has a substantial amount of people. The Platte River, a substantial amount. Access is one of the reasons for this. Those places that are heavily fished tend also to be fairly accessible. For example, not a lot of fishing going on in the backlands or the wilderness areas and the difficult to get to areas of the Wind River Range. The quality of the streams for fishing is another determinant, I think, of this. And a later sequence of maps will show fishing quality in the various streams around the state. Generally, fishing quality tends to improve on a stream just downstream from a reservoir. So as we go through the major reservoirs right through here, large pockets of fishermen start showing up. Similar type of map, showing in this case canoeing, rafting. The Snake River drainage, the vicinity in and around Jackson Hole, absolutely dominates in terms of fishing, canoeing and rafting. Power boating and water skiing, the lakes and reservoirs being obviously dominant. One of the things, we apparently had some people who told the truth, even though perhaps it was not in their best interest to do so. I noticed that we have some skiers and power boaters in Yellowstone Lake, which I don't think is allowed. Perhaps one of our most ambitious digitizing efforts. This shows the major aquifers of the state. The browns and yellows and greens, which form the bulk of it, are the sedimentary aquifers, generally yield high water yielding aquifers. The reds are alluvial. These are aquifers that follow streams. Again, generally high water yielding aquifers. The blues and the grays, the blues and the grays, well, back up. The grays are the volcanic aquifers, which don't carry water. In fact, they're more aquicludes than aquifers. And the blues are more of the same, the granitic ones. And so we have more or less at a glance the places where it makes sense and where it doesn't make sense to sink wells. And of course, the basins are the major places for doing that. This shows potential groundwater contamination caused by humans. The blue, which form the bulk of these, are pumping stations for injecting water into oil wells. Now, I stress that these are not necessarily sources of contamination, but they're potential sources of groundwater contamination. By far, the blue pumping stations make up the bulk of this potential contamination. The red are uranium mills, the yellow trona mills dominating out here in western Sweetwater County. The orange, mostly just up around Casper for the most part, are petroleum refining sites. These are hazardous waste sites. The yellow are facilities that have been noted as being sources of hazardous waste. The orange, down here, it's a local homegrown Superfund site, I believe having to do with the, correct me if I'm wrong, but I think it's the Thai plant. Yeah, okay. And the nominated for national a nominated national priority is the red up there in Casper, and I'm not really sure exactly what that is. Ron, do you know? Brookhurst, I think. Brookhurst, okay. Okay, this is groundwater contamination due to natural causes. The green represent fluorides, the red selenium contamination, blue are fluorides and radionuclides, orange are the radionuclides. Such contamination is pretty much strictly a function of the basins. We don't have it in the mountains, we have it in the basins. Speaking of the basins, let's go on to the basin maps. These are at a different, or these will be in the atlas at a different scale. They're larger. This allows us to focus and present more detail in each of the basins. What we've done is, in fact, divided the state up into 4 regions, focusing on a basin in each one. And on here, we're going to have to redo the color scheme somewhat and emphasize some of these lines. But the bulk of the little yellow lines that you see are average quality type fishing streams. The ones that are the funnest are these blue. These, we chose blue because they are the blue ribbon streams. And obviously, probably from where you are back there, you can't really see those lines. This is a sequence that we'll have to fatten up the lines, brighten them up to effectively do our job, I think. But for the fishermen and fisherwomen amongst us, these may be the most exciting maps that we present. Just quickly, this is the northeastern portion of the state, the Bighorns right here. The southwestern portion of the state. Again, well, you can sort of see the stretch of the green. That's a blue ribbon trout stream. And here's the southeastern portion. This, for those of you who are fisher people, might want to head for that part of the Platte if you haven't already fished it out already. That's quite accessible, and very good fishing. Finally, to wrap things up, on a computer you can put anything you want on top of topography, so I thought I'd wrap it up with this. Water is a very key element, very important element to the state of Wyoming. We hope by the creation, presentation, finally the distribution of this water atlas, that we can better illuminate the policy issues and better illuminate the debate on those policies in the years to come. Thank you very much. One comment, the atlas will not be issued as a series of slides. It will be a standard kind of thing. Will open out along the wideway. The format will be 9 by 12 inches, very high quality glossy paper. The blow up of the slide and enlargement of the slide on the right hand side, the accompanying text on the left hand side. And we hope for distribution sometime late next spring, early summer.
At a premium cost.
At a premium cost.
Larry, do you want to take some questions? And
Sure.
If there's anyone that has a question, if you'll use the red button by your microphone, we'll get that on the videotape as well.
Yes?
Have you thought of making slides available for people that might want to purchase the slides along with the atlas?
I don't know if we thought of it, but it certainly is an excellent idea and would be very easy to do. We would have to work out the copyrights. Neither of us owns it. They're owned by the Wyoming Water Commission, Water Development Commission, and we would certainly be amenable, but don't know whether they would be. Yes.
Is the data such so that you can service requests for maps similar to these for smaller areas? Like if somebody came to you and wanted to do their thesis area or something like that?
Yeah, I teach a course in computer mapping. One of the things that we do in that course is, I didn't bring any of the slides, but students quite often combine it with a thesis or whatever. We have a database for Wyoming and a couple of degrees surrounding Wyoming that has an elevation every 200 feet, which is fairly detailed. For very selected areas of the state, I think we've only got some 17 or 18 out of about 2,800 possible ones. But for these very selected ones, we have a 30-meter ground resolution. So those tapes can be accessed, and you can make maps, yes. I said I was going to pass these out. Why don't I, if you would do that, Nick. Yes.
Do you have an estimate of what it will cost per copy for the atlas?
The cost depends upon how many copies are made, and that hasn't been fully resolved yet. The highest it would cost would, I think, be on the order of, I hope I'm not speaking out of turn, but I don't think it would cost more than 50. And that would be based on, well, maybe 55, something like that. That would be based on producing 1,000 copies. If we were to produce 2,000 copies, the cost would effectively be cut in half, almost. It's that sort of a thing. So the decision as to how many copies to make has not been made. We have been given more or less a fixed budget for the production, and that would allow us to produce at least 1,000, 1,500 or so. We would like very much to see the cost brought under $30. Yes.
Just a thought. I thought the maps with all the silos were a little bit confusing because of the changing units.
Yes.
I wonder if you thought about maybe making the silos different colors or something if the scales were different.
Yeah. The bright orange against the green background seemed like a good idea when we only originally had one or two maps. but it becomes sort of, I don't know, Halloweenish or Christmasish when you see them one right after the other. So I think we'll be experimenting with different color schemes, and certainly your suggestion is a good one. Again, that's an advantage of doing it on a computer. You can quickly make those kinds of changes.
Well, if there are no more questions, thank you again, Larry, and
My pleasure.
we'll see everybody next week.